Okay, so we are going to flip this class today, which means I'm going to give you a little introduction to p-values, and then in class on Tuesday, we will start the class with a short quiz about this video, and then we use the rest of the class for sort of activities, some coding in R, but also some considerations of p-values, some considerations of the people who develop the concepts that we apply in terms of p-values, and some issues that we are seeing today. Awesome. So first thing, there are a number of readings that Mikulski goes in terms of the p-value, and I'm sure all of you guys know the phrase p-value, though we may not fully appreciate what it is telling us. Do note, as you read Mikulski, he is highly critical of the concept, and his criticisms are fair. I mean, in many ways, what I will be encouraging you guys to do is to use p-values as a starting point, never use it as an ending point, never use it as a final point. It's where we begin in terms of understanding patterns. So while I definitely appreciate Mitulski's criticisms, I think they might be just a little bit heavy-handed. So a p-value is a confusing concept for a variety of reasons, and we'll talk about that. But first and foremost, it is the probability that rejecting the null hypothesis is a mistake. And we got to get our heads around that. There are only a few things that you have to memorize in this class, and this is one of them. You have to know instantaneously that when you're looking at a p-value, you're evaluating the null hypothesis, which means we need to remember what that is. Two, you're determining whether you can reject the null hypothesis. And three, whether rejecting the null hypothesis is a mistake. You've got to have those three things down. They just have to make sort of intuitive sense to you. You just have to go for it. So what this is telling us, as these examples illustrate, if you get a p-value of 0.42, then there is a 42% chance of making a mistake by rejecting the null hypothesis. If you get a p-value of less than 0.01, then there's less than 1% chance of rejecting the null hypothesis mistakenly. So again, there are three pieces about this. We are one, we are valuing the null hypothesis. We are two, we're determining whether we can reject it. And we are three, determining whether rejecting it would be a mistake. If it is a 42% chance of making a mistake and rejecting the null hypothesis, then we tend to accept the null hypothesis. If there is less than a 1% chance of making a mistake when we reject the null hypothesis, then we tend to reject the null hypothesis and describe the alternative. So the p-value tells us what to do with the null hypothesis. Once we decide what to do with the null hypothesis, we can then decide how we want to look at the data and how we want to evaluate that data. Now, in p-values, we're going to start seeing things like one-tail and two-tail, and these describe different properties of our null hypothesis test. In a one-tail null hypothesis, we start off with a prediction that one of our two sides is greater. So this might be the large side, and this might be the small side, and we determine before we collect any data that we expect one side to be greater. What that does is that increases the area to which we can reject the null hypothesis. There are benefits to it, there are weaknesses to it. One benefit, if you have a very small sample size, this can be an approach that allows you to look at the data. Two, if you know exactly what's going to happen, because really this is a part of the study that is just repeating procedures that have been done time and time and time again, then you could do a one-tail with pretty good confidence. By comparison, there's a two-tail. This is where you divide that p-value into two halves of our distribution, where you're not making a prediction because the ultimate answer could be that the large size is greater or that the smaller size is greater. And in this case, what we do is we reduce the amount of area that we can use to reject the null hypothesis, but we use both sides of our distribution in terms of evaluating that. This has some very clear benefits, and except for incredibly rare conditions, this is what you'll use. It is a more conservative approach. It is a more objective approach because before you do your study, you're not making predictions about the pattern that you will see. Instead, you collect the data, you analyze the data, you evaluate the data, and then you let the data tell you what those patterns are. Now, p-values are confusing as hell. Again, they describe a very simple property. The probability that when you reject a null hypothesis, you are making a mistake. But that's weird. And it really is weird if you think about it, because what it means is that we're using statistics to evaluate something we don't care about. And that is no pattern. I mean, true, sometimes that's actually really interesting, and some of the best science has been things that really do not produce biological patterns or random patterns. But for the most part, you don't go into science because you're trying to look at random. You're not going into science because you don't think something's going to happen. But when we use statistics, this is what we're evaluating. We're evaluating the random pattern. We're evaluating the pattern that there's no difference. We're evaluating the pattern that there's no correlation. This is what the stats do. This is not the way, though, that we tend to think about as scientists. We tend to think about predictions. We tend to think about expectations. We tend to think about if you add this stimulus, you're going to see this response. So that's strange. In addition, the p-value is not the endpoint. In fact, a lot of people get really excited by saying there is a significant pattern. No, no, that's boring. In fact, that's just where you start. The p-value is the first place that we use the statistics. And then we want to look at the distributions. We want to look at comparisons. We want to look at the overall patterns. Figures become very important. Confidence intervals become very important. Overall differences, overall correlations become very important. P-value is not the ultimate concept. It just tells you the first step. Where do you go next? In fact, you can almost think of it like as choose your own adventure. The first thing you do is you look at the p-value, and that determines whether you're going to describe patterns or whether you're going to describe no differences. If it is a significant difference, you describe the patterns. If it's not a significant difference, then you describe no difference. It's where we begin. In addition, a p-value tells you the probability of making a mistake by rejecting a null hypothesis. It does not tell us the probability that the alternative hypothesis is true. We infer that if we reject the null hypothesis, and that is fair. But it doesn't tell us the probability that it's true. So 1 minus p is not equal to the probability of a real difference, a real pattern, a real correlation. It's how we will describe things, but we're not using actual number to tell us the strength of the alternative hypothesis. We can describe the alternative hypothesis, but the number does not tell us that overall quantitative strength. Finally, the p-value is not telling us the probability that the null is true. It doesn't. It's why we have that really goofy phrase, we fail to reject the null hypothesis, which is a difficult concept to get your head around. The p-value only tells you the three things. It evaluates the null, it tells you the likelihood that you can reject it, and the probability that you're making a mistake by rejecting the null. If you fail to reject the null, it doesn't tell you that the probability of the null being true. Instead, it says that unless we have really, really good evidence of a pattern, we're going to treat any differences we see or any correlations we see as random. Another thing, a p-value of 0.05 versus a p-value of less than 0.05 are not the same thing. Less than 0.05 means that there is a smaller than 5% chance you'll make a mistake if you reject the null. A p-value of 0.05 means that there is a 5% chance of making a mistake if you reject the null. In class and in my own writing, I tend to describe all p-values exactly until they become less than 0.001. So if a p-value is measured out at 0.036, like you see right here, or measured out at 0.002, then I write out exactly. P equals 0.002. However, if the p-value is really small, let's say the p-value is 5.2 times 10 to the negative 10. That's a tiny number. That's 0.000000005. I don't know how many zeros there are. It's tiny. That's basically zero. I don't bother with that. That's so small. We're really confident if we can direct null. In those cases, I just average it out to p is less than 0.001, which just means there's a really, really, really small chance we're going to make a mistake if we reject the null. So, what is so significant about a p-value of 0.005? This is a threshold. In fact, you are taught to memorize this threshold. You must use 0.005. Anything above that, you fail to reject the null. Anything below that, you reject the null. Yeah, it's kind of weird. There's some logic to it, but most of people just sort of take this number as an arbitrary faith-based number. The logic to it is that it sort of gives us a threshold for committing a type 1 error. And a type 1 error is when you fail to, it's what is it? It's a false positive. You describe a pattern that doesn't really exist, right? Um, where do we get it? Well, we got it in two parts. We got it from a guy by the name of R.A. Fisher, and he wrote two things. One is a little bit arbitrary. The second actually makes a heck of a lot of sense, and it's pretty logical. The arbitrary one is basically the p-value of 0.00, I'm sorry, p-value of 0.05, this threshold number, means that you have a 1 in 20 chance of making a mistake when describing a biological pattern. It's kind of like odds. If you have a 1 in 20 chance of making a mistake, are you willing to take that chance? And R.A. Fisher said, yeah, I can take that chance. And because R.A. Fisher said it, and R.A. Fisher is one of the people who started biological statistics and really all the stats that we use, in addition to developing the modern synthesis that unified genetics and evolutionary biology, we accept what he said. That makes sense. Now, his logic was a little deeper than that. What he noted was that 0.05 basically is a number that is more than twice the standard deviation in a normal distribution. So he's working with idealized data, that bell curve, and he's saying that if we can go beyond 2 standard deviations, then we're probably pretty comfortable in rejecting null. And one, that's logical, and two, that has quite a bit of reason. Now, R.A. Fisher is a complicated person, and ultimately, he's a bad person. And we'll talk about that in class. And actually, we'll have a little conversation about how do you deal with a situation where the knowledge, the insight, the ideas that come from someone who really has a highly problematic history. So, on Tuesday. Finally, two more points. One, ultimately, the p-value is just where we start. And it's just where we begin in terms of describing sort of biological statistics. Once we look at the p-value, we then describe the descriptive statistics, confidence intervals, figures to describe whether there are real patterns or not. It is the starting point. We can describe no patterns. We can describe patterns. Both of those are biological interests. It is biologically interesting when we do not have a factor that influences, and it is biologically interesting when we do have a factor that influences. It depends on the question. The p-value is step one. It is never the final step. And to say something of significance is it's illogical. It doesn't make any sense. It's a relative statement, one, so it's an adjective. So it has to describe something that's significantly random, significantly different. Two, it doesn't give us any additional information, and that's really unsatisfactory. That's in fact, it's kind of like a teasing. There's so much good information, and we stop at sort of the most trivial and boring step. Finally, a word of caution. Overemphasis of p-value can be highly misleading and sort of create some pretty problematic and at times dangerous, really depending on the type of study that's being done. It is really important to know what it is. It's really important to know what it is not. And it is absolutely critical not to make strong, hard decisions based on it. It is the beginning. It is a very useful tool, but it is only where we begin in terms of our overall analysis. Okay, on Tuesday, we'll continue on some different ideas. We'll play around with some R. And again, we're going to talk about a Fisher. He's interesting and a little terrifying. Have a good day. Oh, remember, there'll be a quiz at the beginning of class, therefore you need to see the video because the quiz will be based on the video.